All right. So we originally started right here with the nature of waves, and we've worked our way down through. I know it's been several days since we've done any of this, so I'm just kind of refreshing your memory. Remember, waves carry energy, wave properties, and there's two different types of waves. Remember the transverse waves, compressional waves. There are crests and troughs in a transverse wave. They carry energy at right angles. And longitudinal waves have compressions and rarefactions. Then there was trough, the wavelength, crest, amp. We went all over that. If you need to watch my notes again or my lectures, please do so. It'll help you out. You'll understand all these scribblings and whatnot. Okay? And that brings us to the behavior of waves. The behavior of waves. Okay. All right, the behavior of waves. Reflection. If you are one of the last people to leave your school building at the end of the day, you will probably find that the hallways are quiet and empty. When you close your locker door, the sound echoes down the empty halls. Your footsteps also make a hollow sound. Thinking you are all alone, you might be startled by your own reflection in a classroom window. The echoes of your image looking back at you from the window are caused by wave reflection. Wave reflection. Without wave reflection, you could not even see the lockers in your school hallway. And you can see the girl here. What's happening is the light hits her face, and then the light bounces off of her face into the mirror, and then the light bounces off the mirror into her eyes. So I have 1, 2, 3 different reflections going on just by looking in the mirror. And these are light waves. This is a light wave that's reflecting in this case. Okay, and what happens here, let me get my pen out. Wonder what color we're on. Okay, green will be fine. Okay, so what's going on here is this. The angle of incidence always equals the angle of reflection. So the angle of incidence is always equal to the angle of reflection. So if we draw a surface, and this is true for a tennis ball bouncing off the floor. It's the same for light waves, sound waves, whatever the angle of incidence, and we're just going to 45 degrees. Why not? We'll just say 45 degrees. That means it will reflect at 45 degrees. It is known as the law of reflection. The law of reflection is when my angle of incidence right here, always equals the angle of reflection. Okay. Now things change when you get it more into advanced physics. You may be looking at something like this. 45 degrees. It is not going to bounce off the surface at a 45 degree angle. It's going to be different because I have to consider this angle here. But again, when we get in there, we're talking about advanced physics. All you need to know is for the law of reflection, the angle of incidence always equals the angle of reflection. Okay? The law of reflection. The beam that bounces off the mirror is called the refracted beam or the reflected beam, and the line drawn perpendicular to the surface of the mirror is called the normal. Oh, this would be the normal right here. This area right here that splits those two, that's known as the normal. And we can see it right here. Okay, there's my normal, my angle of incidence. There's the flashlight, the angle of reflection, boom. They're always going to be equal to each other. According to the law of reflection, the angle of incidence is always equal to the angle of reflection. Right here, this is the important one. Okay, we'll take that off there because it's kind of smearing it. But there you go. Refraction. Now what happens here is as a light beam, Let's just change color. Why not? I don't know. Yellow. We're talking about light beams, so let's do yellow. Okay. So what happens if I have, let's say I have a block of glass. Okay. Here's my block of glass. As light comes down and hits this block of glass, the light beam is going to slow down. When it slows down, it changes its angle. When it comes out, it's going to go right back and speed up to where it was before. Okay, this is called refraction. When the light slows down, and remember, we have a normal here. Here's our. Let me change the color for the normal. Boom, 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 boom. Orange, why not orange? Hopefully, it's not too close to yellow. Here's my normal. Oh, here's my normal coming down through the middle of this. Okay, so when the light beam hits and slows down, when it hits and slows down, it's going to bend towards the normal. Okay, wish I could get a straighter line. I'm sorry, these lines are so crooked, but it bends towards the normal. Boom. And then once it leaves, it goes back to its original angle. I don't know if I can get this or not, you guys. I'm trying to use a straight edge here. And it goes back to its original angle. But it's going to bend towards the normal. Okay, here it is. The light comes down, hits, and it bends towards the normal. That's what gives it this funky effect with the straw in the glass of water. Now, if I am, in this case right here, and it's kind of, let me just redraw this. Maybe it'll help if I redraw it a little bit. I'm going to change my block of glass to different color. So here's my block of glass. Okay. And I know this is showing water, so it might be a little confusing. I'm going to show you what happens though. Again, we'll go with orange for the normal. I'll put the normal down through here. And again, I'm going to try to use a straight edge. There's my normal. Okay. Now, when this light beam, I'm going to draw both of these. I'm going to draw both of these figures into one. Okay. So what happens here? I'm going to try to get. All right. Here comes my light beam. When it hits and is refracted, it's going to bend when it's entering this area. It's going to bend towards the normal. Okay? It's bending towards normal. If you look, it's going at this angle. It hits, it changes a little bit and bends toward the normal. Let me try to make this even more so. Let's try this again. Again, I'm trying to use a straight edge, so it's a little bit strange here. There. Now it's bending towards the normal. When it exits this object, this piece of glass, as you can see right here, it bends back away from the normal. Okay? So when it comes to right here, it's going to now bend away from the normal again and go more perhaps the way it originally entered. Okay? So you have this refraction. Boom. Bends towards the normal, bends away from the normal. Okay? And again, in this case, my normal is right here. This is the normal. That's the center spot, or that normal. All right. All right. And here's another example. When somebody's in the pool and you're standing here, sometimes it looks like they have two sets of legs. That's because not only is it reflecting in here, it reflects back to your eyes. And it can really mess with your mind, okay, which is going on right here. Okay, that brings us to diffraction. Diffraction. All right, sorry about that. My dogs were going crazy. Diffraction. Diffraction means it kind of bends around a corner, or you can see it here. It's the bending of a wave. It's the bending of the wave. If you look right here, here comes my wave. Here's my wavelengths. You can see the crests and the troughs are darker. Crests are a lighter color. And as they move in this direction, boom, they're going to be diffracted because of the opening. All right. And if you notice, they get squeezed together and they come through here. They start doing this kind of thing and spreading out again. All right. With that in mind, the worst place you can stand if you're trying to listen to somebody talking out here, put somebody out here talking to their friend. Hey, hi, what's going on? Not much. Don't stand right here. You'll never hear anything. Okay, you don't want to stand here. You can't hear it. You want to stand where you're going to be able to hear it. Okay, you'd be better standing across the room. Over here, you'll hear them better because of the way it diffracts. Okay. If you look, and this will even be more, and sometimes we want to diffract these wavelengths. If you see this, there's no waves here. If you go down to the Clear Fork River, if we go down to the Clear Fork River, so I'm going to change to blue for the water. We're going down to the Clear Fork River. There's a little white house that sits here. Okay. I don't know how well I can draw. There's this little white house sitting here. And then there's this sandy area, and then there's this sandy area here. And the Clear Fork River comes around here, and then it curves around the road. Okay. What's happening is as this water flows in this wet direction, and I think you guys know where this is, real close to the Mickey mark down here where I have this little white house in this little sandy area. So what's happening is as this water comes, it's eroding this bank. It's eroding this bank right here. All right. So what they've done is they've put out here what's called a groin. And what they're trying to do with that groin is they're trying to make the water hit this and then turn really sharp right here. So it's not cutting into the bank here. And if you've noticed, and I know you have, when the water really starts running and it gets high and it's running fast, this groin causes a lot of the water to go through that section of the woods and completely skip this. That's the whole point of this groin right here. It's to diffract. It's to diffract that water to get it to quit tearing this bank up and eventually tearing into the road. So diffraction is bending of the waves, okay? And it can be all kinds of waves, water waves, sound waves, light waves. And that's what we're getting at right here. Here's hearing around corners. Here's diffraction of radio waves. Make sure you're reading this because they all work about the same way. It's just different types of waves. Now we have interference. There's two different types of interference. There's constructive interference and destructive interference. So if we take a look here, blue and yellow make green. This is constructive interference. As long as the crests and troughs line up, I can add these waves together. And when I add these waves together, I get green. Blue and yellow equal green. Notice how the wave is larger. All right. I can have destructive interference. Destructive interference is when the waves, the crests and the trough line up and they're opposite of each other. Then they cancel each other out. So in this case, here's the blue and the yellow. They have to be subtracted, and that gives us our green. That's constructive and destructive interference. Standing waves. Standing waves. In a standing wave, and if you've ever heard of, if you're in music and you've heard of an octet, you can get 8 waves on a string. Okay, 8. I should say you can get more than 8, but they are unequal. 8 equal waves on a string. These are called nodes. Let's see if we can see. Yep, nodes, where it's smashed together. Oh, the 8 waves on a string, that's where the octave comes from. Octave. I don't know if it's an octave. In 8, there's 8 C notes on a piano, 8 G notes, 8 whatever. Okay, it's because you can get 8 waves on a string. So these are nodes, and these, where it's spread out, are called antinodes. Okay, so nodes and antinodes. And a standing wave is a special type of wave pattern that forms when waves equal in wavelength and amplitude but traveling in opposite directions continuously interfere with each other. Standing waves have nodes, which are located where, well, I show you where it's these small spots here, and the antinodes are there. And then it goes on to tell you about standing waves in music, and like I was telling you, the octave, okay? Resonance means if I have two waves that are exactly, let's just say I have tuning forks. Those are going to be garbage tuning forks, but I'm trying. Here's my tuning forks, okay? And let's just say these tuning forks are in the key, have a C key. If I hit this one, bam, with a hammer, and I make it vibrate, okay, it's vibrating. I don't know what I'm doing here, but if I get these close enough, that vibration moving through the air will cause this also to start vibrating. This one will also start vibrating, okay? So we'll just go with that for now, and I believe that is going to be it for this lecture on behavior of waves.